So we've got, you're looking at the notes for limiting reactants, and I don't think you need to write all of this down. This is just background information for you here. But we've been assuming to this point that when we were doing these problems with conversions, that you have unlimited resources. So if I gave you one number, you're assuming that will be the thing that runs out first. But of course, in reality, if you're going to take two or three or four things and mix them together to do a reaction, in reality, one of those things runs out first. And the thing that runs out first, we call the limiter or limiting reactant. It limits how much of a particular thing you can make. Okay, so imagine bicycles, and the only two things you need to make bicycles in this example are one frame and two wheels. Well, if I had 10 wheels and three frames, and I needed to start making bicycles, I would stop after the three frames because the frames run out first because I need two wheels for every bicycle. I'm going to have some wheels left over. In fact, if I had 100 wheels and three frames, I'm still only making three bicycles. And chemistry works the exact same way. If you take two amounts of something, two different things, and then you react them, one of them is going to run out first. The thing that runs out first limits how much product you can make. Okay? And we're going to look at a couple of examples of that and how to solve those problems. The good news is solving those problems is very easy. It's a thing that you already know how to do. The bad news is you have to do that thing twice. Lucky. And I'm going to, oh no, my three got displaced. I'm going to do the problem, and this is definitely something you want to copy down. I'll give you a second to do that right now. But I'm going to do the problem, and then I'm going to kind of label all of the pieces of it, like give you all the definitions and things. But really the best way to do these kind of problems or these notes is for you to just jump in with the problem, and then I'll show you what everything means. So take a second to copy the first example down there. I'm going to move this 3 where it belongs. As you're writing it down, you can see that these problems look different than problems we've done in the past. And the reason that you're going to tell them is because there are two numbers in this problem. When all the problems that we had done previously, there's only one number. Okay, so as I read this problem, it says how many grams of NH3, that's ammonia, are produced when 25 grams of nitrogen react with 20 grams of hydrogen. Now, one of these things is going to run out first, okay? And it's not always the smaller number, okay? Because you have to get into, it's not the grams that matter, it's the moles and the mole ratio. So you can't just look at it and say, oh, obviously hydrogen's going to run out first, because you don't know that, because these reactions are based on mole ratios. So you have to convert them and do two three-step problems. And the rule is simple. So if you see two numbers in the problem, do two three-step problems or three-step conversions to get them to figure out how much of something you make. So it's the math is something that you've already done before, which is nice. I'll do it for you also right now. So I'm trying to figure out how many grams of ammonia I make, 25 grams of nitrogen, 20 grams of hydrogen. Take my 25 grams of nitrogen, I'm going to convert that into grams of ammonia. This is a thing you already know how to do, a three-step problem. We call them mass problems. And we are using this template. I'll come back to that in a second. Right here. Nope, that's not it. Be cool. Here we go. This template. Down here at the bottom. Yay. Okay. With mass problems. So you've seen this before. Take a picture if you want to have this out to use it today. We're just doing this process twice. We're going to figure out which one of these two things runs out first and how much ammonia we make as a result. So you've seen this already, which means I can go a little bit faster through it. Here we go. So start with the molar mass of nitrogen. It's 14 times 2, so 28 grams of nitrogen. That came from the periodic table. First step. Second step is mole ratio. So I'm going between nitrogen, which is right here, and ammonia, which is right there. And then you can see it's a 1-to-2 ratio. 1 mole of nitrogen will give you 2 moles of ammonia. But you want your answer in grams, so figure out how many grams of ammonia are in 1 mole. So 1 mole of ammonia is 14 plus 3, 17 grams of ammonia. That number came from the periodic table as well. So we're going to do that one. We're going to do the exact same thing. I just did nitrogen, but now I'm going to do the exact same stuff with hydrogen. So let's do that also. Take my 20 grams of hydrogen. And I know there are 3 steps. I like to write that out first. You don't have to. Say 1 mole of hydrogen, again from the periodic table, is 1 plus 1, so 2 grams of hydrogen. And then mole ratio for hydrogen to ammonia is a 3-to-2 ratio. So 3 hydrogens will give us 2 moles of ammonia. And then finally, 1 mole of ammonia is still 17 grams of ammonia. Okay, so the way the setup is something that you should be familiar with at this point. We've been doing mass problems for our 3rd week now. So all of these should be where the numbers came from, mole ratio, all that stuff should be, again, something that's second nature to you. Okay, mathematically, multiply by everything on top and divide by everything on bottom. So in the first one, take 25 times 2 times 17 divided by 28, and I got 30.36. And the other one, I take 20 times 2 times 17 divided by 2 divided by 3. I got 113.33. Okay, now here's where the words come in, what all these numbers mean. Okay, these problems, as I mentioned, are limiting reactant problems. And the only thing that matters is the smaller number. The smaller number right there, watch these highlighting skills. We call that the theoretical yield. That's not how you spell it at all. That's how much you would make if everything went perfect. Okay, you never get to the larger number. It never happens. Bad. Okay, once you get to 30.36, the reaction's over. It stops, and the reaction stops because something ran out, and the thing that ran out is right here. Okay, we call that the limiting reactant. It runs out first and gives you the smaller number. Okay, you're going to have some hydrogen left over, right? Because all the nitrogen will be gone, used up. And when it's used up, you get to the 30.36 grams and the reaction stops. You're going to have some hydrogen left over. That's why we call hydrogen the excess reactant. Some of it will be left over. Okay, you can actually calculate how much, but it's a pandemic, so we're not going to worry about it right now. All we're going to try and figure out is how much of something we make. So to answer this question, how many grams of ammonia are produced? The smaller number is your answer to that question. We call these limiting reactant problems, but you can see in the problem it didn't mention limiting reactants anywhere, but that is the kind of problem that this is because we have two things. One of them runs out first and limits how much stuff we can make. Questions about where any of the numbers came from or what they're called? You can ask in the chat. The nice part is, as I mentioned, it's all math you know how to do and things you've done before. The bad part is that it's twice the work for the same level of answer. The other kind of common question you get asked with these is what is the percent yield of the reaction? So the 30.36 highlighted in pink, that's what would happen if everything went perfectly. Okay, if you did this reaction in lab and it was set up perfectly, the most you could make would be 30.36. But you know things go wrong in lab, and you have sausage fingers, maybe you spill something, whatever. A lot of reactions don't even go to 100%. Okay, so for whatever reason, for reasons you don't care about in this class, but that would be the most you could make. So sometimes you get other questions that tag along with these limiting reactant questions that are percent yield questions. And in percent yield questions, which you can see right here, they tell you what you actually made and then ask you what percentage is that. Okay, so like any other percent yield or percent question, it's what you actually made divided by what your theoretical yield is. I'm going to rewrite that. Actual divided by theoretical. And the theoretical is above in pink. Oh, and you multiply that by 100. And that is how you set up. The actual has to be given to you in the problem. Okay, I'm going to highlight it there. The theoretical is what you found in the previous problem. I'm going to highlight it like that. Okay, that's how you know where the numbers come from. So the actual is given to you. Or if we were not in a pandemic and we were in lab, you could actually do the lab yourself and find your actual yield. But it's pandemic, so we're not. We're in our learning dungeons. Okay, so take your 28 grams That's not cool. And then divided by what you were supposed to make, which is the 30.36 grams. Multiply that thing by 100. Get your percent yield. So 20H divided by 30.36 is equal to 92.2%. Is that right? Yeah, 92.2%. So we made 92.2% yield in this reaction. Okay, we didn't quite get to 30.36. Okay, and again, it's hard to say if that's good or bad. Some reactions just don't go to 100%. I mean, if you were getting something below 90 and we were in class, I would make you feel bad about it. That's my job as a teacher. But in reality, a lot of reactions don't go that far. Any questions about any of the numbers, the two kinds of problems?